On December 3, 1987, Soviet Air Force strategic aviation units at Olnya Air Base on the Kola Peninsula prepared for a routine long-range patrol mission over the Barents Sea. The base, located approximately 1,800 kilometers north of Moscow and 200 kilometers south of Murmansk, served as a primary staging facility for Tu-95 Bear bombers conducting reconnaissance flights along NATO maritime approaches. Soviet operational doctrine presumed these aircraft departed monitored airspace under conditions providing substantial tactical advantage. American early warning radar installations positioned along the Arctic frontier operated under fundamental physical constraints imposed by Earth's curvature. Conventional ground-based systems achieved maximum detection ranges between 200 and 250 nautical miles against aircraft flying at typical strategic bomber altitudes. Soviet aviation planners calculated that formations departing Olnya enjoyed approximately 90 minutes of undetected flight time before entering surveillance coverage approaching Icelandic airspace or the Greenland-Iceland-United Kingdom gap. That operational assumption, validated through decades of Cold War patrol missions, had become catastrophically obsolete. American intelligence officers at North American Aerospace Defense Command headquarters inside Cheyenne Mountain tracked the Soviet bombers from the moment they lifted off from Kola Peninsula runways. The surveillance capability that shattered Soviet operational planning emerged from exploitation of atmospheric physics that conventional radar systems ignored entirely. Radio waves propagating through the lower atmosphere travel in essentially straight lines, until encountering significant discontinuities in the refractive properties of the medium through which they move. Earth's curvature creates a horizon beyond which ground-based transmitters cannot direct electromagnetic energy toward targets flying at altitudes below approximately 40,000 feet. A radar installation positioned at sea level theoretically detects an aircraft at 30,000 feet altitude when that aircraft reaches approximately 245 nautical miles distance, the geometric horizon determined by the planet's spherical geometry. Soviet strategic aviation operated under the reasonable presumption that American surveillance systems faced insurmountable physical constraints preventing detection of aircraft departing bases, positioned more than 1,000 miles beyond the Arctic Circle. The ionosphere, an electrically charged atmospheric layer extending from approximately 50 to 250 miles above Earth's surface, provided the mechanism through which American engineers defeated those geometric limitations. The Air Force Rome Air Development Center initiated fundamental research into over-the-horizon radar applications during the late 1950s, investigating whether high-frequency radio transmissions could provide useful surveillance capabilities through ionospheric reflection. The ionosphere comprises several distinct layers characterized by varying electron densities resulting from solar radiation ionizing atmospheric gases at different altitudes. The D layer exists between 50 and 90 kilometers altitude, absorbing high-frequency transmissions during daylight hours. The E layer spans 90 to 150 kilometers, providing reliable reflection of signals in the 5 to 15 MHz range. The F layer, divided into F1 and F2 components, extends from 150 to 400 kilometers, reflecting frequencies up to 28 MHz under favorable conditions. Radio waves transmitted toward the ionosphere at appropriate frequencies and elevation angles refract back toward Earth's surface at distances determined by transmission frequency, ionospheric electron density, and the geometric relationship between transmitter location and the refracting layer. Experimental systems demonstrated that carefully engineered transmissions could achieve detection ranges exceeding 1,000 nautical miles through single-hop ionospheric reflection. When radar energy reflected from the ionosphere struck aircraft surfaces, a portion of that energy scattered back toward the ionosphere and reflected again toward receiving stations positioned on the ground. This bistatic configuration, employing separated transmitting and receiving antennas rather than the monostatic arrangement where a single antenna performs both functions, enabled detection of targets at ranges where Earth's curvature placed those targets far below the radio horizon as calculated for conventional line-of-sight propagation. The Advanced Research Projects Agency funded development of experimental over-the-horizon backscatter systems through the 1960s. By 1970, sufficient technical maturity existed to justify transition from laboratory demonstrations to operational prototype construction. The first operational over-the-horizon backscatter installation, designated AN FPS-118, began construction in 1975 at sites in central Maine selected for their favorable ionospheric propagation characteristics and minimal radio frequency interference from commercial broadcasting stations. The transmitter facility near Moscow, Maine, incorporated 12 CW2250 transmitters manufactured by Continental Electronics, each delivering 100 kilowatts of continuous wave output. The transmitters drove 6 separate linear phased array subarrays, each optimized for specific portions of the 5 to 28 MHz operating frequency range. The complete transmission array stretched 3,630 feet in length, comprising vertical monopole elements mounted on steel towers with a wire mesh backscreen extending 65 feet behind the radiating elements. The backscreen, constructed from corrosion-resistant galvanized steel wire in a configuration resembling chain-link fence material, functioned as a reflector directing transmitted energy toward the ionosphere rather than wasting power in radiation toward terrain behind the antenna. Engineers positioned the receiving facility approximately 100 miles southeast at Columbia Falls, Maine, to optimize geometric relationships between the ionospheric reflection point and the bistatic baseline separating transmit and receive sites. The receiving array measured 4,980 feet in length, incorporating 246 fan monopole antenna elements mounted on 65-foot towers with an identical 65-foot wire mesh backscreen. Each monopole element connected to dedicated low-noise preamplifiers and signal processing channels that preserved phase relationships across the array aperture. Digital beamforming techniques enabled simultaneous formation of multiple receive beams covering the surveillance sector, with adaptive processing algorithms suppressing clutter returns from ocean surfaces and terrain features while enhancing faint aircraft signatures. The system achieved effective radiated power reaching 100 megawatts, despite actual transmitter output totaling only 1,200 kilowatts, a power gain of approximately 49 decibels, resulting from antenna directivity concentrating transmitted energy within the coverage sector. The East Coast radar system achieved initial operational capability in January 1986, with a single 60-degree surveillance sector covering maritime approaches from the North Atlantic through Arctic regions accessible to Soviet bomber formations. Operations personnel at Bangor Air National Guard Base in Maine monitored displays presenting target tracks correlated with known flight plans filed by commercial aviation and military training missions. Uncorrelated tracks, aircraft detected within the surveillance volume that did not correspond to expected traffic, generated alerts transmitted to North American Aerospace Defense Command and Strategic Air Command headquarters. By December 1987, the installation operated with 360-degree sectors providing 180-degree coverage from due east through north to due west, establishing a surveillance arc extending from European approaches through Greenland and Arctic routes to Pacific maritime corridors. The system routinely detected and tracked single aircraft at ranges exceeding 1,850 nautical miles, with maximum demonstrated range reaching 2,000 miles under favorable ionospheric conditions. The West Coast radar system employed refined second-generation technology incorporating lessons from East Coast operations. The transmitter site near Christmas Valley, Oregon, positioned in high desert terrain, minimizing ground conductivity losses that degraded transmission efficiency in electrically conductive soil conditions. The receiving installation north of Alturas, California, incorporated larger antenna apertures optimized for enhanced small target detection capabilities. Both East and West Coast systems employed tropospheric scatter communications, links transmitting processed radar data to operations centers where IBM 36065 mainframe computers, among the most powerful data processing systems available during the mid-1980s, analyzed track files and generated tactical alerts. The computers processed approximately 50 megabits per second of raw radar returns, applying Doppler filtering to separate moving targets from stationary clutter and tracking algorithms correlating sequential detections into coherent flight paths. Soviet strategic aviation planning throughout the 1970s and early 1980s operated under assumptions validated by operational experience accumulated during thousands of patrol missions flown since the late 1950s. American interceptors based in Alaska challenged Soviet aircraft regularly, but those intercepts occurred only after bomber formations crossed into Arctic airspace, approaching the North Warning System radar line, extending across northern Alaska and Canada. The interception timeline provided Soviet crews with substantial tactical flexibility. Aircraft departing Kola Peninsula bases flew established routes along the Arctic Circle rim toward Iceland, maintaining altitudes and flight profiles designed to maximize fuel efficiency during missions lasting 8 to 12 hours. The presumption that American surveillance could not detect these aircraft until they approached within 250 miles of forward radar installations shaped operational planning, crew training procedures, and tactical doctrine governing how bomber formations would respond to interceptor challenges. The AN FPS-118 network fundamentally invalidated those assumptions. On March 14, 1988, a Tu-95 Bear bomber departed Olnya Air Base at 4:12 hours local time, beginning a routine patrol mission, planned to transit along Norwegian Sea approaches toward the Greenland-Iceland Gap. North American Aerospace Defense Command Operations Centers detected the aircraft approximately 11 minutes after takeoff, when the bomber reached sufficient altitude and range for backscatter returns to propagate through the ionosphere with adequate signal strength for processing algorithms to establish a coherent track. The detection occurred at a range exceeding 1,650 nautical miles, more than 6 times the maximum range achievable with conventional ground-based radar systems. American intelligence officers monitoring the track correlated the flight path with known Soviet patrol patterns, assessed the mission as routine reconnaissance, and authorized fighter interceptor squadron alert crews to begin pre-flight procedures. By the time the Soviet bomber crossed into Icelandic airspace 8 hours into its mission, American F-15 interceptors had been airborne for 30 minutes positioned along the projected flight path. The transformation in strategic warning timelines represented a paradigm shift in air defense operations. Conventional early warning systems provided approximately 10 minutes warning time for supersonic aircraft and 30 minutes for subsonic bombers, intervals barely sufficient to scramble interceptors and position them along probable approach corridors. The AN FPS-118 increased warning time to 90 minutes for supersonic threats and 3 hours for subsonic bomber formations. This extension enabled defense planners to adopt more deliberate response procedures, evaluate threat assessments with reduced time pressure, and position interceptor forces with tactical advantages that shortened engagement timelines. Soviet aviation units discovered that American fighters appeared with disturbing regularity along flight paths that should have remained unmonitored until bomber formations crossed into conventional radar coverage. Alaska-based air defense squadrons accumulated extensive operational experience intercepting Soviet aircraft throughout the Cold War. Between December 1961 and the late 1980s, Alaska Air Defense Command squadrons flew 306 successful intercept missions, challenging 473 Soviet aircraft operating from forward bases across the Barents Sea. The overwhelming majority of these encounters occurred in Arctic regions, where compressed hemispheric distances positioned American and Soviet territories only 50 miles apart at the Bering Strait. Soviet Tu-95 Bear bombers and Tu-16 Badger reconnaissance aircraft routinely probed American air defense response times, testing radar coverage patterns and evaluating interceptor deployment procedures. American F-4 Phantom and F-15 Eagle fighters conducted visual identification passes, photographing Soviet aircraft to document specific variants and external configurations that intelligence analysts used to assess upgraded capabilities. The operational environment in Arctic regions presented unique challenges that influenced both American surveillance capabilities and Soviet operational planning. Aurora borealis, the northern lights resulting from solar-wind interactions with Earth's magnetic field, generated electromagnetic interference that degraded over-the-horizon radar performance during periods of intense auroral activity. The charged particles creating visible auroral displays also produced ionospheric disturbances that disrupted high-frequency radio propagation, temporarily blinding surveillance coverage in far northern regions. The North Warning System, a network of 52 unmanned radar installations extending across Arctic Canada and Alaska, provided complementary surveillance filling coverage gaps where ionospheric conditions prevented reliable over-the-horizon detection. The integration of line-of-sight early warning radars with long-range over-the-horizon systems created a layered surveillance architecture that Soviet aviation could not defeat through tactical routing or operational timing adjustments. The precision limitations inherent in ionospheric reflection techniques prevented over-the-horizon radar from supporting terminal guidance for interceptor engagements. Target location accuracy measured several miles, sufficient for strategic early warning functions, but inadequate for directing fighters to visual acquisition range. The ionosphere functioned as an imperfect reflector characterized by spatial variations in electron density, temporal fluctuations driven by solar radiation cycles, and geometric distortions resulting from irregular layer boundaries. Radio waves reflecting from this dynamic medium experienced phase shifts and propagation delays that introduced angular errors and range uncertainties into calculated target positions. Operators employing over-the-horizon radar for initial detection and track establishment handed off targets to conventional precision tracking radars as aircraft entered line-of-sight coverage, enabling terminal guidance vectors positioning interceptors for visual or radar contact. Atmospheric conditions influenced optimal operating frequencies across the 5 to 28 MHz spectrum available to AN FPS-118 transmitters. The ionosphere exhibited maximum usable frequency characteristics varying with solar activity levels, time of day, and seasonal changes affecting ionization rates in the reflecting layers. Operations personnel continuously monitored ionospheric conditions using oblique-sounding measurements, diagnostic transmissions probing reflection characteristics at multiple frequencies to determine which bands provided optimal propagation for surveillance missions. The system automatically adjusted transmit frequencies based on sounding results, selecting bands that maximize detection range while minimizing clutter interference from meteor trails, sporadic E-layer reflections, and other propagation anomalies that generated false target returns. The strategic impact of over-the-horizon radar extended beyond tactical advantages in specific intercept missions. Soviet military planners confronted the operational reality that their bomber forces no longer enjoyed sanctuary periods during departure from forward bases. Every strategic aviation mission launched from Kola Peninsula facilities faced immediate detection and continuous tracking throughout flight profiles that previously remained unmonitored for hours. This surveillance transparency eliminated tactical flexibility that Soviet doctrine presumed available for mission abort decisions, route adjustments responding to weather conditions, and coordination timing with naval surface forces operating in contested maritime regions. American intelligence analysts gained unprecedented insight into Soviet strategic aviation operational patterns, training activities, and readiness postures through continuous monitoring of bomber movements. The AN FPS-118 program consumed substantial resources, reflecting its strategic importance and technical complexity. Procurement costs totaled approximately $177.7 million per sector, with military construction expenditures adding $10 million for site preparation and facility construction. The East Coast Radar System, with 3 operational sectors, represented an investment exceeding $550 million, excluding research and development costs, absorbed through earlier experimental programs. The West Coast installation added comparable expenditures. Plans for an Alaska radar system incorporating 2 sectors monitoring Pacific approaches and a central radar system with 4 sectors providing 240-degree southward coverage from north-central United States locations received congressional funding authorization through fiscal year 1989. The Alaska system would have closed surveillance gaps across Barents Sea approaches, while the central installation provided coverage of southern maritime corridors and potential cruise missile attack routes approaching from Caribbean and Gulf of Mexico regions. Budget reductions implemented as Cold War tensions diminished terminated expansion plans before construction commenced on Alaska and central sectors. The dissolution of the Soviet Union in December 1991 eliminated the primary strategic threat that justified over-the-horizon radar network operations. The Air Force initiated phase-down procedures in April 1991, reducing operational schedules and placing both East and West Coast systems into caretaker status with 12-month recall capability. By October 1992, the installations that once operated 12 hours daily tracking Soviet strategic aviation entered mothball status with minimal maintenance crews preserving equipment against potential future reactivation. The operational personnel, specialized technicians, and intelligence analysts who had monitored Soviet bomber movements dispersed to other assignments as the mission that defined their professional expertise evaporated. Alternative mission applications briefly extended operational life for over-the-horizon radar capabilities. The National Oceanic and Atmospheric Administration collaborated with Air Force Operations Centers between 1992 and 1994, employing FPS-118 backscatter measurements to map ocean surface wind fields and current patterns. The same ionospheric reflection techniques that detected aircraft also revealed sea state conditions through analysis of Doppler shifts in radar returns from moving ocean surfaces. Meteorologists tracked several Atlantic hurricanes using over-the-horizon radar data, demonstrating that the technology provided valuable environmental monitoring capabilities, extending beyond its original military surveillance mission. These applications generated scientific research benefits, but could not justify the substantial operational costs required to maintain the installations. Counter-narcotics operations provided another mission justification beginning in 1994. The East Coast Radar System resumed operations at reduced schedules, typically transmitting at least 40 hours weekly with detection data forwarded to Drug Enforcement Administration coordination centers and Coast Guard operations facilities. The surveillance coverage extending across Caribbean approaches and Atlantic transit routes theoretically enabled detection of aircraft smuggling narcotics from South American production regions toward United States coastal entry points. The operational reality proved less effective than mission planners anticipated. Drug trafficking aircraft typically flew at extremely low altitudes below optimal over-the-horizon radar detection thresholds, employed small single-engine aircraft presenting minimal radar cross-sections, and operated during periods when ionospheric conditions degraded surveillance performance. By 1997, operational costs for counter-drug missions, consuming millions of dollars annually for maintenance, personnel, and utilities, became prohibitive relative to the limited detection successes achieved. The FPS-118 network entered cold storage with 6-month recall status, requiring maintenance sufficient to enable operational restart within 180 days if strategic requirements emerged justifying system reactivation. That recall timeline gradually extended as budget pressures intensified and alternative surveillance technologies matured. North American Aerospace Defense Command confirmed in June 2002 that no operational requirement existed for over-the-horizon backscatter radar capabilities. The strategic threat environment had transformed fundamentally since the systems achieved initial operational capability in 1986. Terrorist organizations replacing nation-states as primary threats employed tactics that over-the-horizon radar could not effectively counter. Satellite surveillance systems provided global coverage without the atmospheric limitations constraining ionospheric reflection techniques. Conventional air defense radar networks offered superior target location accuracy for homeland defense missions within United States airspace. The Air Force initiated environmental assessment procedures in 2005 examining options for permanent deactivation and equipment removal from the Maine, Oregon, and California sites. The massive antenna arrays, comprising thousands of tons of steel towers, wire mesh backscreens, and transmission line infrastructure, presented substantial environmental remediation challenges. Local communities near the installations expressed concerns about economic impacts from facility closures and requested consideration of alternative uses for the sites. Preservation advocates argued that the installations represented significant Cold War heritage warranting documentation through the historic American Engineering Record Program. The Library of Congress completed comprehensive documentation in 2006, recording technical specifications, operational histories, and photographic surveys preserving detailed records of the technology that once provided America's longest-range surveillance capability against Soviet strategic aviation. The legacy of over-the-horizon radar development extended beyond the specific FPS-118 installations that entered cold storage. Australian Defence Forces deployed the Jindalee Operational Radar Network employing similar ionospheric reflection principles to monitor maritime approaches across northern Australia and eastern Indian Ocean regions. The system achieved operational capability in 2003, demonstrating continuing relevance of over-the-horizon surveillance for nations requiring wide-area coverage across vast oceanic distances. Russian military forces maintained several over-the-horizon installations, including the Container system, deployed near Gorodets providing coverage across European approaches. Chinese defense planners invested in over-the-horizon radar development, reportedly achieving operational systems monitoring Western Pacific maritime regions and tracking aircraft movements across Southeast Asian airspace. The fundamental physics enabling over-the-horizon detection, ionospheric reflection of high-frequency radio transmissions, imposed operational constraints that technology improvements could not eliminate. The ionosphere remained an imperfect and dynamic reflecting medium characterized by temporal variations, spatial irregularities, and propagation anomalies requiring continuous monitoring and adaptive system adjustments. Aurora interference in Arctic regions created surveillance gaps during geomagnetic storms. Target location uncertainties of several miles prevented precision tracking applications. Yet within those constraints, over-the-horizon radar delivered strategic surveillance capabilities that conventional systems could not approach. The ability to detect aircraft at 2,000 miles distance transformed air defense timelines and eliminated tactical advantages that Soviet strategic aviation had presumed guaranteed. The confidence Soviet planners invested in geographic sanctuary, the assumption that bomber bases positioned deep within Arctic territories operated beyond American surveillance reach, collapsed when over-the-horizon radar revealed every departure from Kola Peninsula airfields. The operational flexibility Soviet doctrine, anticipated from 90 minutes of undetected flight time, evaporated as American intelligence tracked formations from takeoff through mission completion. The billions invested in transmitter arrays, receiving installations, and data processing facilities demonstrated American commitment to technological solutions addressing strategic problems. The FPS-118 that eventually entered cold storage after the threat it countered dissolved had already achieved its strategic purpose. Soviet aviation commanders learned that nowhere remained invisible when American engineers exploited atmospheric physics to defeat Earth's curvature.